the divergence of a vector field is a number, a scalar quantity associated to the vector field that is calculated in this way. We calculate the partial derivative respect to x of the first component, respect to y of the second component, and respect to z of the third component. The addition of these three partial derivatives is a function that depends on x, y, and z, but is a scalar function. So we have a number associated to a vector field. And we are going to have a number for each point x, y, and z. Well, this number is going to have an interpretation, especially in physics. So for instance, if the vector field we are talking about represents a fluid, so if the vector field represents the velocity to which the fluid is moving, so then the divergence measures the tendency that the fluid has to collect or disperse at the point. So if the divergence at a certain point is a positive number, so we could say that the vector field is expanding. If the divergence at a certain point is negative, so we could say that the vector field at that point is compressing. So in other words, when the divergence is positive, so we can say that the vector field is divergent from the point. In other words, we could say that at the point, more fluid is flowing out than flowing in at that particular point if the divergence is positive. And in the other way, if the divergence is negative, we could say that more fluid is flowing in at the point than the one that is flowing out. Okay, so in order to remember this calculation, we could consider the operator given by just the derivatives. I mean, just the act of calculating the derivative, right? Observe that there is no function here. So we could consider this operator that means to do the derivative respect to x, y, and z. And if we multiply this formal vector dot product, the actual components of the vector field, so then we are going to have the divergence. So we can consider that the formula that we were given before is just the dot product of this operator times p, q, r, right? That are the components of the vector field. And if we remember this as a dot product, so we could remember also that the result of the divergence is a scalar. It's not a vector, but scalar. Okay, so let's calculate, for instance, the divergence of this vector field in general, and then we can calculate it also at a particular point. So to calculate the divergence then, we need to calculate the partial derivatives of each one. So the derivative respect to x of the first one, the derivative respect to y of the second one, and the derivative respect to z of the third one. Okay, so let's calculate each of these derivatives. The derivative of this respect to x, well, the y goes out, and the derivative of x squared is 2x. The same way here, the derivative respect to y, the z is a constant, and the derivative of y squared is 2y. And in here, respect to z, the x is a constant, and so we have the derivative of z squared is 2z. So we have the three derivatives. Now to calculate the divergence of this vector field, we have just to add these three quantities. So the divergence will be the addition. So this function, which is a scalar, right? So the results are numbers. This function is the divergence at each point. So if we want to calculate at a particular point, so let's say, for instance, how much is the divergence of this vector field at the point, let's say 1, minus 2, 3. Well, let's pick up the function here and evaluate at 1, minus 2, 3, x, y, z. Okay, so following this formula, here will be 2x, y plus 2y z plus 2x z. Okay, so this is the minus 4 minus 12 plus 6, which is minus 10. So we got that at this particular point, the divergence is minus 10, meaning that at that point, there is more fluid flowing in than flowing out. The second object associated to the vector field is going to be the curl. Now, the curl of a vector field is going to be another vector field. I mean, remember that the divergence was a scalar function. The curl is a vector field. So we associate then to a vector field another vector field. And this new vector field is calculated in this way. We're going to have to take this component of the vector field and do the derivative respect to y. And then we take this component and do the derivative respect to z. And then we subtract them, and so on. In order to remember this formula here, we can consider the curl as a cross product. If we consider as before the operator given by just the symbols of the partial derivatives, if we now do the cross product with f, we are going to obtain exactly this formula that we described before. So let's calculate it that way. So the curl of f is actually the cross product, which is calculated writing the ajk, and so here we are going to put the operator of the partial derivatives and here the components of the vector field. So, and here the components of the vector field, that in this case are p, q, and r. So when we expand now this determinant, we obtain exactly this. So this will be I times, when we eliminate the row and column of I, we get just this determinant here. So let's calculate this determinant. This determinant will be this minus this. So this is derivative respect to y of r, right? That will be this product, minus this, which is minus derivative respect to z of q. That's the first component. You see that that's what we have here. And so on. So you continue calculating this cross product, and you will get then the three components of the curl. The curl of a vector field also has an interpretation in physics. The curl is going to measure the tendency of the fluid to swirl at the point, to rotate at the point. And considering that the curl is a vector field, we have more than a quantity here. We have a quantity which is the magnitude of this vector, and this quantity is going to measure how much is this tendency, right? If it's a lot or if it's a little. But also, since this is a vector, it has also a direction, and the direction is going to indicate the axis around which the vector is rotating. Let's calculate the curl of this vector field. The curl of f, as we said before, is the cross product, where we put here the derivatives, and we put here the components of the vector field, that in this case are xz, xyz, and minus y squared. And now we calculate this determinant. So this will be I times, And so the first determinant, which is this one here, will be the derivative respect to y of minus y squared. Minus this one here is the derivative respect to z of x, y, z. That's the first component of the curve. So the second component, we're going to continue writing here, minus j times, and now when we eliminate these two, we're going to have this times this minus this. So this is going to be derivative respect to x of minus y squared minus derivative respect to z of xz. That's the second component of the vector field curl. And then we are going to have the last component, that is when we eliminate this, the determinant of this will be this minus this. And so in our case, it will be the derivative respect to x of x, y, z minus the derivative respect to y of xz. Okay, and so now we just calculate these derivatives. So the derivative, the first component is going to be the derivative respect to y of minus y squared. Well, this is just minus 2y. Minus the derivative respect to z of xyz is just xy. Okay, that's the first component. The second component is the negative of this, right? Because of this minus here. So it's going to be minus, and let's calculate the subtraction. The derivative of minus y squared now with respect to x is 0, right? Because y squared is constant respect to x. Minus derivative respect to z of xz is going to be just x. Comma, the third component is this derivative. The derivative respect to x of xyz is just yz, minus the derivative respect to y of xz is just 0. And so the vector is minus 2y minus xy, comma, this is minus minus x, this is just x, comma, and this is yz. So this vector field then is the curl of this other vector field. We have some results related to the curl and the divergence that make sense physically and also algebraically. We can prove actually these results essentially using the Clairaut theorem that says that the mixed partial derivatives coincide. So for the first result says that if we do the curl of a vector field that happen to be the gradient of a function, so this is going to be 0. So we can prove this by just writing down what the curl of the gradient is. So it means that is derivative of f respect to x, derivative of f respect to y, and derivative of f respect to z, right? So that will be the gradient. And if we now do the curl of this, so we will be doing here So when we calculate the curl of the gradient, so we are going to have this determinant. Observe what we will get in each of the components. So for instance, when we do the first component, we eliminate this, and we're going to calculate just the determinant that remains. Well, observe the determinant that remains. We're going to have here the derivative respect to y of the derivative of f respect to z, which is the second derivative of f respect to y and z. And when we do the other one, the one that we have to subtract, so we are going to have the second derivative of f respect to z respect to y. And so, by the theorem that we have seen before, that the mixed derivatives are equal, this is going to be 0. And in the same way, you can see that all the other components of the curve are going to be 0. So this is the vector 0, the one that have components. This is going to be 0, 0, 0. In the same way, we can see that if we do the divergence of a curve, so the result is also going to be 0. And I would encourage you to actually do the calculations. I mean, write down the curve of f with all its expression, calculate the divergence by just adding the partial derivatives, and you will see that by using the same theorem of the mixed derivatives, you will get that the divergence is equal to 0. In this case, it's the number 0, not the vector 0. And this result that the curl of the gradient is 0 can be expressed in some other way by saying if the vector field is conservative, then the curl is 0. Because if the vector field is conservative, we know that it's the gradient of something, right? And so by the theorem, we know that the curl will be 0.